Clock is going to get set here.
Hello everybody, my name is George. And to my left I have Devin, Javier, and to my right, Guillermo and Ernesto. And we are the Impact Loading and Recovery of Copper team. Now the goal of this project was to design separate projectile and target packages in order to study spallation of copper at different impact pressures. And to achieve this, we would induce shock loading, and we would also use a momentum trap in the target to absorb the release waves caused by the impact. And we would use these results that we got in order to study the correlation between what we predicted and what we actually got in order to study void nucleation and crack propagation. And the image you see is crack propagation as it occurs and the to complete fracture on the right.
Research into the field of high strain rate physics began with the work of Dr. John Hodgkinson. His son Bertram was actually the first one to document how shock waves could induce a fracture in a ductile material. As you can see here in the picture on the bottom left, this is what's known as void nucleation, which is also known as spall. And it's the creation of holes in the material by the shock waves at the grain boundaries. Now this process is dependent on the grain orientation. Now on the right, you can see how the void nucleation propagates until a crack is formed. The holes expand and then they unite until it forms a crack, and then you have separation of fragments from the main piece of material. Now, research into the process of spallation has been conducted at research labs such as Los Alamos and the Russian Academy of Science, and some of their work also outlines the loading and recovery techniques. However, no previous studies conducted at the Air Force Research Lab has focused on soft recovery of the target specimen to perform further analysis. Our shots are going to be designed to cover a pressure range from 1 to 3 gigapascals while trying to maintain a pulse duration of around 2 microseconds. Now we're also going to use a momentum trap to try and reduce or completely eliminate the edge effects on the target specimen. And our goal is to create a void zone of spall somewhere near the middle of the target specimen. Next slide.
Okay, here's just one experiment. These are the 4 pieces that we designed. We have the projectile, the impactor plate, momentum trap, and target. The actual projectile and impactor are one piece downrange in the beginning of the gun. The projectile encases the impactor, and the impactor itself is a variable thickness and also variable material depending on what pressure we're looking for. Then downrange, where the actual impact happens, we have the momentum trap and target. The momentum trap encases the target, and the target is set at a 50-degree angle to help with ease of release. Next slide, please. Okay, here's a diagram of the actual experiment. We have the projectile coming downrange from the barrel of the gun. It is a powdered gun. Comes down. Here's the impactor in the front, of course variable thickness and variable material. It makes planar impact with the target that's encased by a momentum trap, and then it's released into the soft catch recovery system for further analysis. Next slide. Okay, here's a video of the actual experiment. You see here the projectile coming down range, hits the target hits the stripper plate to remove the momentum trap, and the actual target comes down to the soft recovery catch system where it can be further retrieved and then analyzed for metallurgical studies. Next slide. Okay, so our group met every Wednesday in the fall spring semester from 2 to 3 p.m. In that way, we could distribute the workload on the paper and also in the design of the actual experiments. From the paper, we actually had several talks. We had literature survey, wave propagation analysis, design global learning initiative, and future work. And then also for each design of projectile and target package, we had a team leader, a project manager, a designer, and analysis. Next slide. Here's a breakdown of our cost. We have 4 different costs. We have labor. We estimated 289 hours of our work hours at $65 for the 5 team members. Of course, we weren't getting paid. This was a senior design, but this is just to have a more accurate analysis of cost. And that came out to around $18,000, substantial amount. Then implementation. Each experiment cost $10,000 by the AirFRL to actually do the experiment at a cost of $50,000 for the 5 different packages. And then finally, or before, we have travel. We actually traveled to Eglin Air Force Base to meet with Professor House and to talk to him about the experiment and have any questions about our design, he could answer them there. And then we had the materials and manufacturing. The actual copper, the PMMA, all the impactors had to be manufactured and the material had to be bought. And that came out to a cost of $2,300 and to a final total of $70,000.
So upon impact, shock waves will be released and flow through the material. Eventually those shock waves will bounce off of the free surfaces of the impactor and projectile. These bounced waves are now called release waves, and eventually they'll continue to flow through the material and intersect within the target. This intersection is the spall plane. This is what our project is based on looking for. Now our project is based on from 1 to 3 gigapascals, And our spot strength of copper ranges from 1.5 gigapascals to 2.6 gigapascals. Now, we're going to be analyzing the gradual effects for each impact so we can see how the spall reacts in the copper. Now, our pulse duration that we're looking at is about 2 microseconds. And the pulse duration is when the release waves intersect into the target. Now, over here on the right, we have some equations that we used to calculate where the spall plane would actually land. Now, the impact pressure is a function of our density of the material, the shock wave velocity, and the particle velocity. Now, for the material selected for our target, as you can see here, it's a very faint circle. That's our target that we're analyzing. That is, for every experiment, it's going to be made out of copper. The reason why we use copper is because it's a very common material that the Air Force uses in a lot of their applications. Around that is our momentum trap.
That should be it. It should. Yeah, there we go.
All right. So around that is our momentum trap, also made out of copper, and around that the ring holding everything together is made out of aluminum. The momentum trap and the aluminum ring will be destroyed at the end for every single experiment. For our projectile that we have here, we chose a material for the tip. We used either PMMA, which is also known as acrylic glass, or aluminum. PMMA was used to achieve the lower impact pressures because it's more stable, and aluminum was used to actually achieve the spall.
So after we understood how wave propagation occurred during our experiments, we wanted to conduct the first design of PMMA and copper for 1 gigapascal, 2 microseconds of pulse duration, and obtain a spall plane inside the target. So what we have achieved during the mathematical model and applying all the equations, we got a 1.03 gigapascal impact pressure, a 2.04 pulse duration, and we predicted that the spall plane, if it were to occur, would be inside the target at 2.79 millimeters deep. Now, the effects from the momentum trap were negligible due to the fact that it would take too long to reach the target. Next slide, please. So after we ran the first design, we wanted to go the extra mile and come up with 2 design alternatives. Alternative A was based on a constant impactor thickness with 3.3 and 3.5 millimeters. So we ran the mathematical model using these thicknesses and the density of PMMA, and we obtained that 3.3 is the optimal impactor thickness due to the fact that we were able to obtain a spallation plane inside the copper target in somewhere in between the sweet spot of the target itself. So the speeds that we're going to be using are 350 meters per second and 850 meters per second, with a race according to how we achieve the impact pressure from 1 to 3 gigapascals. Now, as you can see here, the pulse duration is going to decrease due to the fact that we're increasing the speed and due to the fact that we're keeping the impactor thickness constant. Next slide, please. So for design alternative B, we wanted to go with a variable thickness impactor, ranging from 3 millimeters for first shot and 3.85 millimeters for last shot. This is due to the fact that we wanted to maintain a constant spallation plane at 3.2 millimeters inside the target and a constant pulse duration due to the fact that even though we're increasing the speeds, we're also increasing the impactor thickness.
This is the current shock recovery system they have set in place at AFRL, and what Guillermo was explaining earlier, the projectile comes into the barrel muzzle at the bottom, hits the target assembly, and they both hit the stripper plate, but only the target goes into the soft catch media. Now what you see here are the first 3 shots. On the top is the recovered target, and below it is the momentum trap. Now for the first 2 shots, you see target is all in one piece, so no visible spall occurred. But for the third shot, you see complete spallation, and it just cut in half. And you see in the momentum trap, in the exploded view, the shock wave actually extended into the momentum trap. You see the line there. Now this is the result of the first shot, which is PMMA on copper at 350 meters per second. Now once the shock wave hit the free surface and the pulse duration, the shock wave pulse is what our advisor is looking for, and that duration lasted for 2.25 microseconds. And the impact pressure was 1.07 gigapascals, close to the 1 gigapascal we wanted. Now, what happened afterwards, we're not sure what it is. It's currently being investigated by AFRL, but we have a various amount of assumptions of what it might be. One might possibly be the gap between the momentum trap and the target due to the glue holding it together. Another possibility could be the physical properties, the physical changes in the properties of the copper itself. And the other possibilities could be the geometry of the 15-degree momentum trap, that angle of the momentum trap. So for the second shot, we actually had an error recording the data. So we had to redo the second shot. So the fourth shot we did,
was the same specifications as the second shot. As you can still see, the shockwave pulse with no spall. Our pulse duration was 2.6 microseconds, and again, we still have the same anomaly after the shock pulse, which is again being researched by AFRL. Our impact pressure is 1.77 gigapascals, enough to start creating voids within the copper, but until actually X-ray examination, we won't know if there are voids created or not. For the third shot, where we actually did have our spall, we used with aluminum and copper. It was shot at 321 meters per second. As you can see here, our shock wave pulse, followed by a pullback and then a spall signal, showing that we had spall. Our pulse duration being 2.75 microseconds, and our impact pressure being 3.54 gigapascals, much higher than the 2.6 maximum spall strength of copper.
So after we received the results from AFRL, we wanted to compare the predictions that we had to what actually occurred in the experiments. So in your left is going to be the impact pressures run at the absolute speeds that we designed for. Now the impact pressure, so what we actually designed to what actually happened is pretty close. There's very small errors between them two. The main error occurs in the pulse duration, and this is due to the fact that the theoretical square wave shock wave that we expected to have is not perfectly square. Now, in order to improve our predictions, we want to use the actual speeds recorded during impact. Now, the impact pressures go closer to actually occurred inside the experiments, but again, the pulse duration was solved due to the fact that those are theoretical improvements that we need to have later.
Now, assembly of the target itself is done using a very well-characterized copper under precise laboratory conditions to try to help ensure a planar impact with the projectile. And disassembly and maintenance of the target and projectile is not necessary because they're one-time use and they're destroyed when the gun is fired. And maintenance of the gun itself is going to be handled by the AFRL, so we do not need to factor it into our calculations. Okay. The materials that we're going to be using, aluminum, PMMA, and copper, are readily available to the AFRL, and their production is not hazardous to the environment. The only source of waste from their production is going to be the machining and the finishing of the parts themselves. The research on extreme pressure conditions is done all over the world. So we used SI units for our calculations and then converted to English units when submitting our results to the FRL, so that the work is available in both unit systems. Now, only U.S. bases will have access to the research for now, but if the Air Force decides to release it to other sources in the future, they can do it because it's available in both unit systems. The techniques from our methods can also be applied to other materials, which is good because this knowledge is going to be useful anytime that high pressure loading is involved. And it's going to help to increase the safety and the reliability of equipment that's used in these situations. Unfortunately, knowledge in this field is not very widespread currently, and there's a lot of things we don't understand, such as how the stress that's caused just as spall begins affects material properties such as modulus of elasticity or yield strength of the material. Next slide. The safety risks that are incurred from firing the gun and doing the experiments are covered by the standard operating procedures in place at the FRL lab, so we don't need to worry about safety when designing the experiments. But what we do need to concern ourselves with is if we achieve a spallation plane that is outside of the desired target area, if we don't generate any spall whatsoever, or if we have complete target fragmentation, which would make it impossible to do studies on the soft recovered target specimen.
So as you have been able to see throughout this presentation, we have been able to successfully load copper utilizing a one-dimensional planar wave upon impact. We have also created an impact pressure range from 1 gigapascal to 3.5 gigapascals, changing the velocity of the target of the impactor and the density of such and the thickness as well. We have also eliminated the release waves created on the momentum chart edges, and that evidence of that is pretty much a clean spallation plate that we got in the third shot. Now, the system, we were able to completely recover all the targets, which is a first by AFRL, and moreover, the design predictions and what actually occurred are really closely related, which means that our mathematical model that we put in place is sound and correct for the next experiment. Now, we have been, next slide please, we have been told by Dr. House, our AFRL advisor, that 15 packages have been manufactured in order to keep conducting experiments. The 4th and 5th shots are going to be scheduled for some time between this summer, and then the next shots are going to be run throughout the year. Now, they want to do this in order to make sure that there's reproducibility of the experiments, make sure that they can get the same results in other labs, in other facilities throughout the U.S. Moreover, after they're done having experiments, they're going to analyze them using photomicrography and X-ray tomography. This picture here from the National Lab, Lawrence Livermore National Laboratory shows how void nucleation would look like in the shock loading experiments. Now, after that, they would be able to produce property traits of how copper behaves under extreme loading, which is what we're looking for. And Dr. House has told us that he wants to study how shock loading specimens undergo quasi-static and dynamic loading after having loaded. Moreover, after this research is performed, the testing of more materials such as aluminum and the more exotic material that is titanium will be conducted. Now, we thank you very much for being here today. Do you have any questions?
Questions?
What's the ultimate end result of, or the reason? Is this for, bullets being fired at something? Is it material that's going to be scattered? Is it aircraft that might get hit by certain things? I mean, why is the Air Force?
Anytime that you have a high pressure impact and it involves ductile materials, it doesn't just have to be copper, it can be applied to other materials. So say you have like some kind of space shuttle like orbiting the Earth, and you can always get impacts with like debris, and then the better that you understand how the impact is going to affect, because you don't always have to have piercing of the material in order to have like fragmentation on the inside that could cause damage to the shuttle. And so that's just like one application. But any time really that high pressure impacts are going to be involved, such as in safety equipment that need to be like near demolition blasts and things like this, you need to understand how this, like a better understanding of this will help to increase safety and reliability.
So for your third shot, how did your prediction of location come out? So you have a location, right, that you think the two waves are going to overlap. Did you guys take a look at the thickness of each side of the target and compare that with your prediction?
Yes, we actually, through calculations, it's between time and distance. So obviously our target was much thicker than our impactor, so that way the shock waves and release waves bouncing off the free surfaces had a shorter amount of time while the shock wave was still going in the target. So we knew it was going to land in the target, it's just where that was the harder part. We were actually off not by much from the actual experiment and calculation.
Just from the diagram that you have there, it looked reasonably close, right? It's on the front end.
I think it was at 2.4 centimeters, we estimated at 2.7.
Yeah, it was like very, very low.
And so do you know the purity of the copper? Because that makes a big difference with
Supposed to
weight
be
propagation.
oxygen-free copper. We don't know the purity.
Yeah, I mean, it's not,
But,
yeah, right. Just curious if you know. Yeah. And then, so the extra stuff, right, the unknowns. How exactly are they measuring that pulse? Where's the location of the pulse measurement?
All right, so what happens is that they have a PDB probe that shoots light very much to the rear surface of the target. So when the impact occurs, the particle speed on the back surface is going to be different due to the fact that it's wave propagating inside the target. So that means that they measure that pulse, that changing in particle speed, and that's how they record it. For the unknown, like we said, there's maybe some reverberation due to the fact that of the 15-degree taper angle, as well as maybe some physical properties that have not been discovered yet on copper, which would be great actually.
That would be great job.
No, you said you have good data agreement. There's good agreement between the data and your prediction. How do you determine that? By just eyeballing it?
No, we actually had error analysis. We weren't able to present it. I guess if you go down, I'm not sure if it's here, but we have a 10% agreement between what actually occurred and what actually happened. It's not really evaluating it. We had the table set up and we conducted experiments. And Dr. House, our advisor, was satisfied with the results, which is even better for us. We also used finite element codes that we had in place for programming that we could actually compare all results to what actually happened and moreover to that as well.
And you said 10%. Was that acceptable?
Yeah, that's acceptable.
That's acceptable?
In this case, so it's very acceptable.
Oh, sorry. So you use finite element code to simulate the wave propagation?
Well, they're using that.
Okay, all right. I was going to say.
They're using that.
Yeah.
You have a question?
Would somebody convert a Pascal to pounds per square inch?
No.
That's about.
Yeah, that could.
Oh, is it?
It passes so.
I just think in pounds per square inch,
I think it's. No, I mean, it's just a conversion.
It's a conversion.
So pounds
It's
is
not something we
megapascal
commit
is
to
6.
memory.
Megapascal is what, 6? All right.
Wait, what was it?
Yeah, Google the conversion. All right, is that it for questions? All right, let's thank our group. Thank you. So, okay, we're gonna move on to Team 6.
6,000.